Hi calculus students! Today we're going to be focusing on trigonometric limits and the squeeze theorem. So we're going to start off today with a warm-up per usual. So go ahead and pause me and take at most about 5 minutes to solve this, and then we'll come back and see what you got. Hello! So you should have tried the warm-up on your own. Now you see I've already shown my answers, so just to walk through them real quick for those who may have missed one of the problems. When we try to solve this limit up here, the limit as x approaches 5 of x over x minus 5, we get 5 over 0, and 5 over 0 is undefined. We don't want to just say that equals 0. It's undefined, which means that there's a vertical asymptote there. So there's a vertical asymptote at 5, which means we need to figure out what is the limit doing to the left and to the right of 5. Is the function both going up along the vertical asymptote? Are they both going down, or are they going in different ways? We have to look to the left and the right. So that's what I did. And essentially my answer is either going to be positive infinity, negative infinity, or does not exist if they're going different ways. So all I really care about is this number going to be positive or negative. So basically when I get to this step right here and this step here, I'm just like, I don't care what that number is, I just know it's going to be positive or negative. Since they're both positive, I have this final answer down here, that my limit overall is going to positive infinity. And then down here we just had to figure out which was an indeterminate form. So just a reminder on this vocabulary word, indeterminate forms are these forms right here. Because essentially those aren't answers. Like 0 over 0 is not any number. Infinity over infinity is not a number. We need to do a little bit more work to figure out what's happening. So that's what an indeterminate form is. A looks like a huge mess, but really we can just plug in 3 and we get a weird answer, but we get an answer. We could put this in your calculator and you get some weird decimal. B is just a little practice for trig, just reminding you of your trig values, like what's tangent of pi, what's cosine of pi. And if you struggled with that, just remember you can always draw the unit circle to be like, what's happening at pi? Well, the coordinates here are -1, 0, and use that to help you out if you struggled with that. But we ended up getting -1 over pi. And then C, our final problem, when I plug in 0 into tangent, you get 0. So here we get 0 over 0, which is indeterminate. So in our last lesson, we kind of figured out what to do if we got an indeterminate form. If you remember when we got 0 over 0 in the previous lesson, the solutions were to factor or to rationalize or to do something algebraic with the problem so that we could kind of figure out what the limit is. Because basically when we get this form 0 over 0, remember that means we have a hole. We have a hole in the graph, but there's still things you can do algebraically to figure out what it is. But if we look at this problem, tangent of x over x, it's not factorable and there's no square root for me to rationalize this problem. So for trig limits, there are some limits that you're going to have to memorize in order to solve a problem like this. So the same tricks don't necessarily work for trig functions. We do have to do some memorizing. So go ahead and pause the video, write these down. These are just functions that you're going to have to memorize. They come up on the AP exam, and yeah, it'll just be easier if you know them. I did add this one over here on the right that wasn't initially included, but take note, it's basically the same thing as this cosine one. The 1 and the cosine can just be switched. So really, it's kind of just like 2 equations you have to memorize. Both of the limits are approaching 0, so it says theta approaches 0, and then we just have one with sine and one with cosine. I do want to flip real quick to Desmos. Where's Desmos? Here you are. So you can see what these graphs look like. So the blue one is the graph of sine of x over x, and the green graph is 1 minus cosine of x over x. And you can see as these limits approach 0, we have a hole. And that's because we have the denominator we have x in the denominator, and as x approaches 0, it's 0. So we have holes here. But you can see graphically that the limit for sine is approaching 1, and graphically the limit for cosine is approaching 0. Okay? So if we just try to solve these by themselves, we would get 0 over 0. But we can memorize what these limits actually equal. Okay? Cool. So if we have these memorized, we can solve a whole bunch of other problems like these. Okay? So let's solve some of these problems. For A, I do want to remind you, the first step you could always try is to just plug in and see if it works. Okay? Because we still have to know how to solve limits just by plugging in, and sometimes it will work, and with part A, that is the case that we have here. So let's see, plugging in, I'd get sine of 0 plus 1 over 3 cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. So this problem, I just get 1 over 3, and I'm done. I don't have to do a special trig limit. Woohoo! Okay, so you really only have to use your special trig limits if you get an indeterminate form, which I can see over here in B is what I would get. If I just tried to plug in 0 here, blah, 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 like this, I get sine of 0 is 0 over 0. Ugh, I have an indeterminate form. So this is when I'm going to be like, oh, I need to use my special trig limits. Okay, so that's what I'm going to do instead. I see this looks really similar to my special trig limit, so I'm going to flip back real quick. Look at this special trig limit. Oh, I'm realizing that you should add this to your notes. We need our thetas in there. My bad. I forgot to rewrite those. So I noticed that the argument of sine is theta and the denominator is theta too. So it always has to work out that whatever is in the denominator just has to equal what's in the argument. So I could rewrite these special trig limits as like the limit as x approaches 0 of sine of, it doesn't matter, they just have to match 1/5 x over 1/5 x. So it's just like whatever is in the argument, they have to match. I could even square this x. Doesn't matter, because what's in the argument matches what's in the denominator. And then the same thing here, I could rewrite this as the limit as theta approaches 0 of 1 minus cosine. My variable is theta, so I just need to make sure to use that, but I don't know, negative 12 theta plus 1. And then just whatever is in the argument, it has to match. And if they both match, then this limit equals 0 and this limit equals 1. Okay? So going back to this problem, really I just need what is in the argument right here to match what's in the denominator. So the denominator is really close, it's just missing 2. So I can solve that problem really easily by multiplying it by 2. But this is an illegal move right now. Whatever I multiply the denominator by, I have to multiply the numerator by as well, right? So this is legal. I'm just multiplying by 1. Totally cool. And so I can rewrite this like so. So this would be 2 times sine of 2x over 2x. And now I see right here is my special trig limit. That thing equals 1, and I just multiply it by 2. So this is my 2 from right there, and then my special trig limit equals 1. So my final answer is 2. I'm going to say C and D are a little bit more difficult really focus on being able to do A and B, but C and D I want to show for students who might need more of a challenge. Okay. So looking at C, again, this kind of looks like one of my special trig limits, but not quite. So like flipping back, oopsies. I can see my special trig limit for cosine doesn't have a square. It's just 1 minus cosine. So this problem here is not written in quite the correct form. However, I can factor this thing. So I see that the top is factorable. I'm going to try to factor it and see if I can make it look like my special trig limit. So this would be 1 plus cosine of x times 1 minus cosine of x over x. And now I actually do have a special trig limit. I can see that it's right here. So there's my special trig limit. And then kind of like how 2 was just being multiplied in the front, I'm just multiplying by 1 plus cosine. That's okay. So now when I solve this, basically I can think of it, if we use our properties of limits, it's kind of like you're just multiplying these two limits together. So this is why that this is totally legal. Right? So I use my properties of limits and just multiply them like that. And there's my special trig limit again. So this equals 1 plus cosine of 0 is 1. 1 plus 1 times that special trig limit is 0. Oh, so it all goes to 0 anyway. So this is 0. So that's just a little bit more challenging. I don't think too challenging though. You just kind of have to manipulate it in order to find the special trig limit. And so this is the problem from the warm-up where we know that we get an indeterminate form here. And so when we get an indeterminate form with trig functions, that means we need to manipulate it to make it look like one of our special trig limits. Our special trig limits are only in terms of sine and cosine, so I'm going to start by rewriting this function in terms of sine and cosine. Okay? So I'm just rewriting tangent as sine over cosine. And now I'm going to turn this into one fraction instead of 2. Okay, this looks a little too much right now. So I'm going to multiply the top and the bottom by 1 over theta to kind of cancel out the theta down there, and so I don't have so many fractions. So this is equal to the limit as theta approaches 0 of sine of theta over theta times cosine of theta. Do you see the special trig limit? Try to find it before I highlight it right now. Do you find it? It's right here. Sine of theta over theta. The argument is the same as in the denominator. So I know that will go to 1. Again, if it makes more sense for you to kind of separate these using the properties, you can separate them out. Be like, here's my special trig limit, and then it's being multiplied times what was left over. So 1 over cosine theta is what's left over. You can rewrite it if you want. You don't necessarily have to. I know this first green special trig limit right there, that is 1 because I have it memorized. And then cosine of 0 is 1. So this whole thing equals 1. Okay. So we were able to solve the problem that in the warm-up we didn't really know what to do, but using our special trig limits, we can solve indeterminate trig limits.